We will be looking at an introduction to what permanent way engineering is, what exactly this field is about, and then we'll look at what are the things that go within this world, within this permanent way world, and what you need to do in order to excel permanent way engineering. So in this session, we will be looking at the following points. I'll give you a brief introduction as to what permanent way engineering is, what exactly permanent way term means, and then we will look into how this world, how this field has actually evolved right from its inception up to the modern age that we're living in now. And then we will go through certain fundamentals that you require in order to excel in this field, in order to consider yourself to be an expert. And then we'll go through few problem solving statements, some case studies that will give you more insights into how problems are to be dealt with, what kind of problems we are going to face in this field. And last but not the least, I will be explaining what this career would look like, what are the opportunities that you would get in this field. So what is Pway? If anyone goes into Google and tries to search this term called permanent way, you'll get a bunch of definitions. Permanent way is described in many ways, but the one that closely relates to my understanding of permanent way is what is shown in the slide. So the term permanent way entails rails, sleepers, and ballast beds, collectively called as tracks. This system is supposed to transport passengers and goods in the most efficient and economic way from point A to point B. So why do we call this as permanent way and not any other term? So what used to happen is in the earlier days, somewhere around 1800s, 1850s, you used to have contractors who used to transport material from one point to other point, goods, transport, spoils for the site that they're working with. They used to lay this temporary systems within their site so that this transportation is enabled within their site. And then once the site is completely constructed, they would change those temporary track systems to a more permanent solution. So that's where the term permanent way has come into consideration. It is also called as track alignment in other regions, but mostly it is related to the term permanent way within India as well as in few other countries like in the UK. If I bring your attention to the left bottom corner, you will see that there is an image which gives you a longitudinal section of how the track system looks like. So at the top, you have the axle wheel. We also call it as the wheelbase. And that is the component that transfers the load that we have from the vehicle or the train onto the railway system. So you see the axle load shown in that picture. That load is transferred to the remaining components of the railway system, which is the rails at the top, followed by those small blocks, rectangular blocks, which are called sleepers, shown in brown. And the rails and the sleepers are connected, are tied in with each other using clips. Below the sleepers, you have material called as ballast. So ballast is nothing but the stone chips that we get from the stone quarry. So they are closely packed together. The size of those stone chips varies from 5 to 7 centimeters in general. So those are packed together and they form the foundation on which the sleepers and the rails sit. And then below the ballast layer, you have the hard ground, which is the naturally formed ground that we have in our world. To the right side, we have another picture which gives you a cross section of how the railway system looks like. Again, at the top, you have the vehicle, and the vehicle is sitting on the wheelbase. The wheelbase sits on the rails and then the ballast. And followed by that, you see that it is sitting on an embankment, which is the subgrade that we talked about. If you imagine how the load transfers from the train to the ground, it is a point load where the wheelbase is in contact with the rails. That point load transfers onto the rails and then onto the sleepers. But the transfer from the sleepers onto the ballast is slightly different. So what is supposed to be a point load gets distributed on that sleeper, and that distributed load again gets distributed onto the subgrade. Now, why you might consider why we need ballast. So ballast is a material which provides a spring kind of a behavior. So when the train moves through a specific area, if it has ballast, because of the load, it will compress in size. And then when it is unloaded, once the train moves away from that area, it goes back to its original position. So there are other forms, other materials that we use in place of ballast that we'll look at it in a bit more detail in the later slides. So, how did this system evolve? There are multiple ways in which we can look at this question. The evolution has happened in multiple facets in terms of material, in terms of the way the system gets operated, in terms of how the design is done these days as compared to what it was before. You can pick up many points when you do a bit of research about this, but the ones that I've highlighted on this slide are the ones which are more prominent. So we'll first look at gauge. So what does gauge mean? Gauge is nothing but the gap that we have between the two rails when they form part of one track. The gauge has evolved from a non-conventional to a standard one. Let me explain what non-conventional means. If you look at when railway system was started, we had various vehicles. We used to have carts which had different wheelbase lengths. So because these wheelbase lengths sit on the rail and the wheelbase lengths vary from region to region because the cart modeling or the cart dimensions are different, we used to have different gauges in different regions and different countries. That's the system that was adopted based on the local requirements in the early 1800s. But now, moving on to the modern era, we see that most of the countries, most of the clients, most of the modes of transport that we have in this current situation, they usually have standard gauge of 1435 because it is driven by the train manufacturing companies. So the train manufacturing companies decide what is the gauge that they want, or the client decides that this is the gauge requirement, and accordingly the manufacturer develops a vehicle that has that wheelbase length of 1435. Moving on to the next parameter, we have the rails. So again, if you go back to 1800s, you would see that the rails were completely made of material wooden. They were completely wooden. But now you'll see that the rails actually have iron as the material. They are converted from rail ingots to an eye-shaped rails, which are quite strong. And then when we move on to sleepers, which is the next component below the rails, you'll see that they have moved from wooden to concrete material. And now these days you see a more organic material used, polyurethane. There are many other compounds that have been tested and tried out. The reason why we move to these kind of materials is because they are more efficient in terms of operational requirements. They have more resistance towards lateral and longitudinal movement. And in terms of manufacturing and also in terms of procurement, they cost lesser to the client. Then when we talk about subgrade, we have seen what ballast means. Before that, we used to have rails and sleepers placed on the hard ground itself. So there has been an evolution from hard ground onto the ballast system, which is kind of a springboard. And now you see concrete slabs being used as the subgrade below the rails and the sleeper, just to make sure that the track is fully fixed. In terms of ballast system, it has the ability to actually move left and right and front and forward because it is not a composite system which can keep the entire track at one place, whereas the concrete slab can. But the con of concrete slab is it is more expensive. It's a one-time investment, but it is more expensive. In terms of operations, you have manually controlled systems, which used to be, for example, you have the station masters who wave their flags, red and green flags when the train is moving along a platform or it's supposed to stop at a platform. Now, these days, you see systems being evolved in such a way that you have a GPS tracker within the train, within the locomotive or the engine, and it is directly connected to the satellite. And someone somewhere in a center makes sure that the information is sent to the vehicle and it is allowed to operate through a certain route or disallowed to operate on that route. So that's how the signaling system or the operations have evolved as well. In terms of the types of railway systems that we have seen, as we have discussed in the previous slide, we had systems which were used primarily to haul materials or spoils, we call them as goods in Indian terms, from one point to other point. But now you see, based on the requirement of or the demand that we have for that specific system, you have various modes of transportation. You have systems which allow you to transport materials even now, but in a more efficient manner. You have intercity travels or interstate travels, and then you have systems that allow you to travel locally as well, like metros, light rails. You also have systems in some cases, say, for example, in airports, where you need to move from terminal A to terminal B. You have rail systems which cater that requirement as well. Those are usually automated, they are not, they are unmanned, and it is a completely different system with different kind of requirements. In terms of power, if you think about how the vehicle is operated within a route, it has evolved from using steam as the base for power to combustion engines. And now you'll see from the power grids through the thermal power, electricity is drawn above the vehicle. And from that electricity drawn, the entire locomotive as well as the entire train body is run on a given route. In terms of designs, you will still see some experts within this world who are less reluctant towards drawing their designs on a sheet of paper rather than using sophisticated tools. We have softwares in this modern era which will allow us to do designs of track alignment, understand all the parameters, all the standards, all the client requirements that we have within it, and allow us to develop a solution which solves certain problems that the client would have. That there is definitely an evolution of how the design can be transpired um, from 1800s to 2000s. And then the most important parameter is construction. The reason why I say this is most important is, as a designer, as a permanent way expert, you can develop designs in whatever manner you want. You have the flexibility. But what is the most efficient method? What is the most practical method? The one that can be constructed on the site is what matters. So unless and until you don't know how construction happens, there will definitely be a gap between how you develop the design and whether it can be constructed on the site or not. So in terms of construction, you would see that we in the modern era see a lot of machines that are being used that allow us to lay the track even more efficiently than what it used to be in the past, which is every sleeper, every rail being transported manually onto the site, laid onto the site, connected all together, and then checked whether they are in the design position or not. But now, with the advent of machinery, you will see that all these things have been automated. They take less time to install. So, this slide gives you an understanding of how the engines have developed over the course of 200 years. Starting from 1800s, you'll see on the top left corner, we used to have locomotive engines which used to run on steam. And then you had various modifications to that as we moved along, the power being drawn by steam itself, but the way the engines were designed is slightly different, with more power, more capacity, more volume to draw the steam and give more power for the operation. And then you we saw a paradigm shift in which the vehicles are modeled in terms of how the power is drawn. But the most important thing, which is not highlighted over here, is the vehicular design, the body, how it is developed. You see, from being a crude rectangular box on the left side, you see it is in a more complicated shape, primarily due to the application of fluid mechanics, aerodynamics to avoid resistance, to improve the passenger movement, lesser time travel through more speed. So that's where fluid mechanics comes into picture. So that's just an illustration of how the system has evolved in terms of locomotive engines. And it's not only about applying track geometry, it is also about seeing the innovations that are happening around us as well in terms of railway systems. As a permanent way expert, you need to understand these evolutions and make sure that you adopt these into your day-to-day routine. So in this slide, I have tried to give you some statistics as to how various railway systems are present at the moment. So to the left side of the slide, you have various metro systems in some of the most prominent cities across the world. I have also shown what are the total miles or the total kilometers of train network they have for this kind of modal transport, the number of stations, the number of lines they have, and these systems are still evolving based on the passenger requirement, based on the population that is growing within the cities. These are just expanding crazily. You see that boom happening within India as well. So it is nothing new to us. In terms of the cost ride per mile, that split is also given as well as the run times. So some of the systems run 24 by 7 because of the demands that we have. Say, for example, a city like Mumbai, there is definitely a possibility that the metros can run 24 by 7 over there in the future because it's considered to be a sleepless city. So moving on to the right side of the PPT, you have the high-speed rail facts. So high speed is nothing but a system which allows you to travel at 250 or more kilometers. So a couple of points that strike a chord with me is the total network of high-speed rail we have within the world, which is close to 30,000 kilometers. That's a massive network. It's not just concentrated in one country, but yeah, in terms of evolution of that system, that has been humongous when it got started, which is 1964. And then you'll see that the highest speed that this kind of system has achieved was in France in 2007, which is around 575 kilometers per hour. But the one that is in operation, the one that generates the revenue, is at a maximum of 320 kilometers per hour. And another interesting fact is that at the bottom of it, you'll see that there is a comparison of the choice that people would make when the time travel is equal to or less than 2.5 hours. 80% of us would choose high speed rail over air transport. So that's a very interesting fact to see that given short time travel, less than 2.5 hours, we would actually choose a railway system over an airway travel. And at the bottom, you have statistics related to Indian Railways based on the gauge that is used. Predominantly, we have broad gauge, which is 1676 mm. You'll see splits given in terms of whether it has been electrified or it has not been electrified, in terms of the total rail length that we have for each gauge. So around 65,000 kilometers of rail network we have within Indian Railways umbrella. Moving on to the next slide, please. The most important question now is for you to be a permanent way engineer, for you to be a permanent way expert, what do you really need to do? I have split it into the three categories. I've converted them into conceptual awareness, software awareness, and the experience that you're going to bank on. So what do I mean when I say conceptual awareness? If we split how track alignment or the permanent way is conceptually designed. So you have three components within it. There's the horizontal component, the vertical component, and the cant component. So cant is nothing but angle of banking when we talk highway jargon. So that's cant. So these three components are paramount for us to develop a track alignment. And if we know exactly what constitutes these three parameters, we have taken the first step towards becoming a permanent way expert. So this is a simple track where you have these three components assigned to it. And once you develop a design, that's it. Now, if we increase the level of complexity, you'll see to the right side under the complex conceptual category, there is an image given. So what if there is a requirement for you to have vehicle moving from one track to the other track? So the image shows you what is the contraption. You have a special unit that allows you to travel from one track to the other track. That's where the complexity increases. Why? Because the geometry over there is very different from what you usually do for a single track. They are highly curved depending on the speed. And there are certain other parameters that we need to check in order to ensure that the passenger doesn't feel any discomfort. If the tracks are both parallel and then they run straight, you have standard drawings for this kind of complex geometries. But when you have tracks which are not parallel, and when you have these tracks going on a curve and also having angle of banking different for both the tracks, that's where the complexity increases. So that's a very challenging problem. And if the client recommends it, you have to develop a special unit over there. That is definitely going to be challenging because it allows you to explore your limits as to how much conceptually you know horizontal, vertical, and candle. So that's the component regarding conceptual awareness. Then we move on to softwares. So I have just provided icons that relate to some of the softwares that we use within the Pway world. So the first icon is MicroStation. The second one is called as Bentley Railtrack, but it is being renamed to Open Rail Designer. These two are part of the Bentley system suite. So Bentley is one company which allows these tools, these design tools for us to develop a track alignment. And the next two icons are the tools given by its competitor, AutoCAD. Sorry, Autodesk. So you have two tools called AutoCAD, which is the drafting tool, and then the Civil 3D tool, which allows you to develop rail geometry within it. And last but not the least, that the last icon must be quite familiar with you all. We have to provide reports, we have to provide calculations, we have to provide evidence to clients saying that the design that you're doing is absolutely right. So Office 365 has powerful capabilities in order for us to allow that to happen. So that is also a must. PowerPoint presentation, Excel sheets, Word documents. These are the most frequently used softwares within Office 365 suite. And then in the last, experience does matter. So what experience does is it tries to link your skills that you have developed conceptually as well as software and allows you to implement those to solve your problems. The more problems you solve, the more complex scenarios you associate with and try to resolve them, the more experience you'll get, the more you'll be considered as an expert. As simple as that. And if you link it up with the construction problems that the construction contractor would see during a given course of renewal works, that will add more advantage to develop a design which is more practical, which is more relatable, and which will be constructed. So here I have given two case studies. The first one is shown over here. So the problem statement says that the client CR is looking for us, the design consultant, to provide consultation services for a line speed improvement proposal on a track route that has many curves and straight elements. So you as a designer, what would be the considerations that you need to be aware of? And what should be our approach in general? So if I was in that situation, what my approach would be is that I would first understand what are the elements that constitute that track geometry. I would see what are the track parameters that allow me to understand the passenger comfort that that existing geometry provides for that given speed. So you have these parameters called rate of change of cant, rate of change of deficiency, cant gradient, which allow us to understand what passenger comfort is all about. So once I understand the existing conditions, then I'll look at improving the speeds, maybe 20%, 30%, 40%. I'll see whether the existing geometry can accommodate that increase in speed whilst not compromising on the passenger comfort. And then I'll also look at options which will make it uncomfortable for the passengers to move, but with slight tweaks to the existing geometry that can be reduced as well. All these solutions can be put together to the client, and based on the deliberations we have with the client, we can choose the most optimal solution, because it is not only about developing a design, it's also related to how much cost that the client would like to take on themselves to construct that solution. So there is a lot of deliberation that happens after that as well. So that's one way of looking at it. Another case study is about an existing track route that is proposed to be electrified by 2025. The route has several overbridges. So in terms of understanding what overbridge is, it's nothing but a rail that is laid underneath a structure. So you have a rail traveling through the structure, and above it you have another railway or maybe a roadway. So that's what overbridge means. And it is known to have clearance issues to accommodate the new electrification system. So as a designer, the question is, what is the solution that you'd like to propose? And would this solution of yours have any impact on the environment? So as a designer, first, what I would try to understand is what is the requirement in terms of clearances. When I say clearances, it is the gap that we would need to have between the track and then the structure. So once I understand that, I will make an assessment of all the clearances that we have for the existing system itself, which is the bridge and the existing bridge and the existing track. Wherever these clearances are not achieved, the solution we have is twofold. Either I can increase the height of the bridge or I can lower the track. It is usually seen that when you try to increase the bridge in terms of increasing the gap, it is a lot more costlier than lowering the track. But after a certain point of lowering, the track cannot be lowered any further because it is a lot more economical. It is a lot more economical to actually raise the bridge itself. So there is a trade-off between the two solutions, and there is a breaking point where that happens. There's a pivot. I would see what is the lowering that we need to achieve that clearance, but it doesn't stop over there. Once I lower the track, if I develop a design which allows us to lower the track, you are creating a lot more problems. So what used to be the existing condition, you are actually creating a depression over there that creates drainage problems. So if there is an onset of rain, it will all get converged over there because you have created depression over there. So the system that you have developed should actually also trigger a drainage design as well. In addition to that, usually the overbridges are within a cutting, not on an embankment. So the rail sits within a cutting, so water will seep and come into the railways. Now, because you're lowering the track, you have to increase your cutting area as well. So that's a trigger to the geotechnical team because they have to develop new earthworks. And then you also have the electrification system itself. So within that confined space, sometimes you will not be in a position to install the support system that you need for the electrification to run. So you need more area for that. So that triggers another aspect of the design as well. So this gives you an understanding of how the railway system is not only about developing track geometry, it is also about understanding the other disciplines that interact with this track alignment as well. So as a PV expert, you are required to understand these multi-discipline details as well and try to develop a solution which ties up with them and which is more economical. So in terms of career opportunities, people who already have experience can have lateral move to the companies that we have shown in this PPT. These companies are multinational companies. They work across the globe and they're also having branches in India as well. So these are well known across the world for engineering services in permanent way. If you're a college graduate, then your entry to these companies would be as a graduate engineer only. But depending upon the skills you pick up, depending upon the experience you show, depending upon the problem solving abilities that you provide, trust me, your upscaling, your career progression will be quite quick because they encourage, there are programs within these companies which allow you to accelerate your career growth. So just keep that in mind. With that, I conclude my presentation. Thank you for hearing.